drift is the main dominant process. Okay, now we'll draw the IV characteristics. Suppose if device is working properly, means whether if device is working properly or not. To test that one, first you have to measure current versus voltage, then only you can estimate the how the device is working properly. If it is working properly, or you need to say change some parameters, or you need to change interface, or you need to clean the materials very properly, or you have to see you have to reduce the contaminations, or interface is good or not between P and N layer. You have to see many parameters. Okay, to while fabricating the device. Okay, suppose this is the voltage, we have taken x-axis, and on the y-axis we have taken current. Okay, so in forward bias condition, it will increasing the voltage from 0 to certain voltage. Okay, slowly it will not increase up to certain voltage. After that it will start rising, increasing the current. Okay, rise, increasing the current. Okay, this is in forward bias condition. Okay, what is happening? So in the forward bias condition, what we are seeing here, like this. Shall I? So I am drawing again here diagram, band diagram. Okay, just a second. It is not a exactly what we want. So here, so I am drawing a little not a perfect one, but it is okay. Okay, this is Fermi level, and this is also Fermi level. This is P and N. Okay, so here see thing. When you are applying some forward bias, means P terminal is connecting to plus of potential, positive potential, and N terminal is connecting to negative potential, right? So forward bias means same thing, right? So here see, initially we are not getting any current. If you see IV characteristics, we are increasing voltage. Suppose here at 0, so we are increasing slowly this voltage, but current is not increased in a circuit. Okay, after certain voltage, it started rising the current. It started increasing the rapidly current. Okay, why? The question is why there is no current even we are increasing the voltage up to certain voltage. Suppose this is, let's take a some VT. Okay, threshold voltage. Let's take a some threshold voltage. Okay, up to this particular voltage, why there is no current is coming in a device? Okay, why? What is the reason for this? Initially, what is happening in we connected device forward bias. So initially we are applying some forward bias voltage, but even you apply some voltage, we are not observing any current in the circuit. Okay, what is the reason for this one? Anyone please? What could be the reason here? What could be the reason? Please see the diagram and think of it. Why? Even you are applying some voltage, there is no current you are observing in the circuit in forward bias up to certain voltage. After that, even if you increase the voltage, it is rising suddenly, it is rising rapidly. Okay, what is the reason for these two things? What is the reason? Come on, please think of it. Any idea what could be the reason?
Sir, the electrons will crossing the barrier that time when the current increase.
Yeah, that is okay. And before that?
Before that, the electrons doesn't have enough energy.
Yeah, very good.
Barrier.
Yeah, very good, very good. Very good, Vishnath. Thank you for answer. So right, that is correct answer. So initially we are applying some voltage here, but whatever once this junction, when you combine PN and semiconductor, there is a junction, there is a depletion region is forming. After depletion region, that electrons should cross that barrier. Okay, suppose here electrons are there. Suppose you want to send here. Diffusion means here you are applying negative voltage to n-type semiconductor. Electron see some potential height, some barrier or depletion width. So even if you applying some voltage, but electrons doesn't have sufficient energy to cross the barrier, or electrons doesn't have energy to overcome this barrier or depletion width. That's why even you are increasing some voltage here, we will not absorb any current. That means there is no current means what? Current is zero means what? There is no flow of charge carriers. No flow of charge carriers, or no flow of electrons or holes. Current is zero means there is no charges, or there is no carriers are moving. Okay, that's mean current zero means. Okay, up to we are increasing small voltage, but still we are not observing any current here. That means no electrons or no holes are doesn't have sufficient energy to cross the barrier, so that the electrons are not crossing the barrier. Energy is not sufficient, so there is no flow of electron. So once you keep increasing the voltage, certain voltage, these electrons getting sufficient energy to climb this barrier, then started flowing electrons in a circuit, or started flowing holes in a circuit, then current is starting increasing. Okay, after that if you keep increasing, more number of electrons cross the barrier and we will get the current like this. Okay, suppose here, see, suppose you are here, if you take a small example here, you have a climb, you have a here a mountain or something like that. So here you have, so if you don't have energy, you cannot climb, right? Suppose if you have sufficient energy, then only you will climb this mountain. Okay. Similarly, here also electrons seeing some barrier or height or mountain, you can say. Okay. To climb that mountain or to climb that barrier, that needs sufficient energy. How they are getting that energy? By giving external voltage, that is forward bias voltage. Okay, once they get sufficient energy, then they will climb or they will cross the barrier. That's why initially we don't get any current. After that, current is increasing in a device. Okay, this is forward bias condition. Now we will see for silicon or germany, this is VT is what you say, threshold voltage or knee voltage. Threshold voltage or knee voltage, you can say whatever you can say. It's at this voltage, electrons getting sufficient energy or holes getting sufficient energy and crossing the barrier. That's why where current is increasing rapidly. Okay, we can see the current in a circuit. Okay, that's why it is you can increase it. So this particular voltage we are calling knee voltage or threshold voltage. Less than this threshold voltage, we will not absorb any current. Okay, current is almost zero. So actually current is very less before this before this threshold voltage. Current is like 10 power minus 12 amperes. This is very less current. It is not zero here, but ideally it is not zero, but very less current, that is order of 10 power minus 12 or 13 amperes. Okay, that is very less current we will observe here. Okay, that means what? Only few electrons only cross the barrier at less than less than this VT, less than this knee voltage. That is why we are saying almost zero, but it is not almost it's not zero. Very less current, very less current is there, like 10 power minus 12 to 13 ampere. Okay, this is the less current. Okay, so this is the forward bias condition. So generally this is like a knee voltage is about like 0.5 or 6.2 for electron volts for silicon. Okay, millivolts for silicon, and germanium it's like a zero point 0.3 volts or 0.3 volts millivolt 0.3 volts like that for germanium. Okay, depends on material. This threshold voltage will change. Okay, threshold voltage will change. Okay, depending on our device performance and device defects. Suppose defects are there, and material properties and many parameters, it depends. Okay, generally for silicon about 0.6 to about 0.6 to 0.7 it will be there, threshold voltage. Okay, volts. Okay, so now we will see in reverse bias condition. Okay, reverse bias also same thing, but here it will be little higher than this threshold voltage, then after certain voltage even we are increasing the reverse bias voltage in. So up to certain voltage there is no current, similarly like in forward bias, because in reverse bias barrier height also very high, so there is no electrons having sufficient energy, so it will current also very negligibly small. Okay, negligibly small. After that, even you keep increasing, electrons gain the energy and overcome the barrier. And this particular voltage here, you what do you say, breakdown voltage. What is this one? Breakdown voltage. Because once you cross this breakdown voltage, okay, there is a rapid increase in the current, so always you should operate device between breakdown voltage and threshold voltage only. Okay, if you cross the breakdown voltage, more heat will be generated in a device, the device will be damaged. So why you are, suppose if you buy any, suppose if you buy any mobiles or something like that, there is a voltage limit. Did you observe any device? Did you observe any devices? There is a
Yes.
marking and voltage range. So you have to operate within that voltage range only. If you overcome, if you cross that range, the device will break. More heat, more current will flow in the device and it will damage. Overflow of current will be there. So here we will also see how this will increasing. So here we are applying some reverse bias voltage. Okay, like this. Okay, so like this we have some reverse bias. Here we are applying negative voltage and this is P and here N. Okay, here we are applying positive voltage. Okay, so what is happening up to here, we know in reverse bias this junction depletion width is high. That's why compared to here, range is high. Maybe this is 1 electron volts, but here knee voltage is always less than 1 volts. Knee voltage, this is VT, but breakdown voltage may be greater than 1 voltage, or maybe about 1 2 volts, maybe 3 volts, depending on our our parameter. It will depends on parameter. This breakdown voltage VBR VZ you write. Okay, VZ GNR breakdown you say. Okay, generally the what you will say, GNR breakdown voltage. Here you say VZ. VZ is higher than the VT. That means what? Why is VZ is higher? Why it is higher? Why it is higher? So why? Because see, you already you know answer, but you are not saying. In forward bias, depletion width is less. That's why even lesser voltage electrons getting sufficient energy. In reverse bias, barrier width is very high. So you need to apply more voltage, then only electrons gain the sufficient energy and cross the barrier. Okay, that is the main reason. Okay, you got it right. In reverse bias, you need to apply more voltage, then only the electrons cross the barrier. That's why GNR breakdown starts very late or higher voltage. Okay, GNR voltage approximately starts greater than 1 voltage, but threshold voltage it should be always less than 1 voltage. Less than 1 voltage only, sorry, less than 1 volts only, it will start increasing for forward bias. But reverse bias, it may be should reverse voltage may be greater than 1 volts, maybe greater than 1 volts or greater than 2 volts, depends on material and parameters. This one is a GNR breakdown. After that, the charge carrier current will rapidly increase here. See, very rapidly increasing compared to forward bias. In reverse bias, after breakdown, the current will very rapidly increase. What is the reason here? Just before also I informed, I told you this one. So here you observe this IV characteristics. This is reverse bias and this is forward bias. See, you observe forward bias curve, it is slowly increasing after VT, after some threshold voltage, the curve is slowly increasing. Okay, but here after GNR breakdown, okay, GNR breakdown, so very rapidly increasing straight line is there. That means very rapidly current is increasing. So what is the reason here? So up to now, up to GNR breakdown, there is no current. That means electrons or holes doesn't have sufficient energy. That's why only very less electrons or less holes crossing the barrier. So we will get very less current up to GNR breakdown voltage. But at GNR breakdown, at particular voltage, the device current is rapidly increasing, very rapidly increasing. What could be the reason for this one? So, okay, you think of it just, okay, see here, instead of going to conduction band, here electrons, just before also I explained. So electron directly jump into the conduction band of N-type semiconductor. So here electrons are leaves the holes and actually they should go to the conduction band of same semiconductor. Suppose if you take P-type semiconductor, conduction band to valence band to conduction band. But here what is happening? If you increase more voltage, okay, more voltage, they will jump into the conduction band of N-type semiconductor. Electrons jumping valence band of p-type semiconductor to conduction band of n-type semiconductor. That's why many charge carriers will flow in a device. So if current is increasing, that more number of electrons cross the barrier. That means current will rapidly increase in reverse bias after GNR breakdown voltage. That means if overflow of current will flow in a circuit, then the circuit will damage. Okay. So here see what is main reason is if reverse bias is voltage keep increasing. So electrons breaking the bonds in p-type semiconductor and jumping into n-type semiconductor from actually valence band to conduction band of n-type semiconductor. So here to here suppose here you have electron break the bond and instead of going same semiconductor conduction band, they are jumping into the or tunneling, mainly tunneling to the other semiconductor. That's why many charge carriers will overcome this barrier. Many charge carriers tunnel this barrier and jump into the entire semiconductor, resulting in a overflow of current. So that's why we are seeing very rapid increase in current. Okay, current curve. Okay, that's why after GNR breakdown we have high current in a device. So you should always operate the device between GNR voltage, GNR breakdown voltage and knee voltage. Okay, this is the operating voltage of the device. Operating voltage of the device. Okay, is it clear to you why it is increasing rapidly? Why it is in there is no current and this thing? Could you understand this? How the IV characteristics? Could you follow? Could you follow?
Yes, sir.
Yes, sir.
So up to threshold voltage. See here, up to threshold voltage there is no current. There is no means very little current is there. That is, electrons doesn't have sufficient energy to cross the barrier. Once you keep applying voltage at certain voltage, they will get sufficient energy cross the barrier. That's why current will flow in a circuit. Similarly, same thing happens in reverse bias also. Also up to GNR breakdown voltage, very less current will be there. That is because here up to this GNR breakdown happens very late, means a very higher voltage compared to threshold knee voltage, because in the reverse bias depletion width is higher. So you need more energy to charge flow from one semiconductor to other semiconductor. After GNR breakdown at particular voltage, electrons gain sufficient energy, overcome the barrier in reverse bias, and after overcome, very rapid current will increase. That means large number of electrons or large number of holes overcome the barrier. We will see very high current because electrons from valence band to valence band of p-type semiconductor to they will tunnel into n-type semiconductor of the conduction band of the n-type semiconductor. That's why very high current will flow from P to N semiconductor. Then we will get the rapid increase in the current. Okay, this is the IV characteristics forward and reverse bias. Okay, depending on these forward and reverse characteristics, you will observe device is perfectly working or not working. Okay, what you have to modify, what are the things you need to change. Okay, that you have to see the IV curve and analysis the device performance. Okay, now you will see diode equation. Okay, diode equation we will see. Okay, diode equation, generally you write I d is equal to I0 and exponential q v by nkt minus 1. This is the diode equation. Okay, diode equation are p-n junction diode equation. I0 is the saturation current, saturation saturation current, or you can write in current density also. This saturation current should always should be less, because this is leakage current in a device. This is leakage current, this is not useful. Okay, this always should less. Okay, then only we will get the high performance device. Okay, and n is there, ideality factor, ideal factor. That means what? Ideal factor means ideality factor or ideal factor, whatever. Okay. Ideality factor means how our device is performing perfectly, how our device is following ideal characteristics of diode, how far this ideal factor mainly describes how our device is perfect. Okay, how our device is perfect, it will explain. Okay, it value may be, okay, it value may be 1 to 2. This value may be n is equal to always 1 to 2. In between maybe 1 or 1 by 2, or 1 by 2 to 1, like depends on. Generally, for an ideal device n is equal to 1. Okay, ideal device n is equal to 1, but it will vary 0.5 to 0.52 or 2, like that generally. Okay, maybe lesser or more, depends on our device. Okay, so if it is n is equal to 1, we are getting perfect device. Okay, so these are the diode equation. Okay, so if they ask any question, first you have to write and one more important, diode symbol is this one. Diode symbol is p-n junction diode symbol is plus and here minus. Okay, this is the diode symbol. P-n junction diode symbol is this one. Okay, if they ask diode, p-n junction diode, just you write formation of p-n junction and forward bias condition, first zero bias condition and forward bias and reverse bias and finally IV. These three things, these four things you have to write. Okay, I think you got it. What is the p-n junction diode and this thing? Okay, shall I? If you have any doubts here?
Sir, will you share second unit